Hello everyone, welcome to this video. My name is Sentinel-1. I'm a Google Earth Engine expert. In this tutorial, I'm going to show you how to calculate soil moisture index using Sentinel-1 images that is not affected from the cloud cover because it uses active microwave to illuminate the target of interest. So, in the first step, we need to select a study area. As you know, the soil moisture is very applicable criteria for the agricultural region. That's why I'm going to use a farmland to do calculations. For example, you can use any region in all around the world because this tutorial is not limited to one specific region of interest. Just I'm using a part of Iran as a region of interest because I'm from Iran and also I have information about the croplands and the different regions, and you can actually select your own region of interest because the data and Earth Engine platform publicly available, and you won't have any problem to deal with this data and use this calculation. So, for example, in the southwest of Iran, there are a lot of croplands here that you can see. Then I'm gonna select a part of this region as a region of interest. Using drawing tools available here, I'm gonna select a part of croplands available here, just like that. Next, I wanna have focus on the region of interest through the map.center object. The map.center object is a function allows us to have focus on the region of interest as a geometry. Then make a new variable to call Sentinel-1 data. Here, a new variable as Sentinel-1 created. Go to search places and dataset and type Sentinel-1. As you can see, Sentinel-1 SAR data is available here and then imported into the code. After that, image collection assigning to the Sentinel-1. Image collection assigning to the Sentinel-1. So define the filters, the time filters or temporal filters and spatial filters that is necessary for the satellite data that provides higher spatial resolution. So here, that filter dates, I'm gonna limit my data to the specific period of region. When you want to calculate the soil moisture using Sentinel-1 data and also according this tutorial, you need to select a period of time that is a little longer than usual because we need to monitor all the fluctuations in the backscatter situation for the region of interest, and because we need to consider the minimum variations and the higher variations for a large period of time, then we can do calculations based on this variation during the time. Filter date starting from time start and ends to time end, just like that. Make two variables for time start and time end. EarthEngine.date, EarthEngine.date. The starting date, for example, is 2017, and time end equals to EarthEngine.date 2002, for example, 2024, just like that. So next, filter bound. Filter bound help us to bound satellite data to the region of interest that is already selected. The region of interest is geometry. In the next step, we need to consider other properties that are important only for Sentinel-1 data. .filter, EarthEngine.filter, .list contains. I'm gonna call those of Sentinel-1 data in which the transmitter-receiver polarization equals to VV. So list contains means in their list of properties I need to I need to use those of data including transmitter receiver polarization with VV condition. So next, Earth engine.filter.equal. Another property for SAR data is instrument mode that should be equals to interferometric widths. These are necessary filters for dealing with Sentinel-1 images. Now I'm gonna get a print to see how many Sentinel-1 data is available for this region. After a few moments, in the right panel, you will have a new image collection, 1,340 elements available here. So now here for each date, there are a couple of bands, VV, VH, and angle. The target band is the VV because it provides higher electromagnetic radiation compared to VH polarization. VV means vertical sending and vertical receiving. The satellite or sensor sends electromagnetic radiation vertically and received dose of backscatters or dose of scattering that's coming back vertically. This is very important. But VH here means sends vertically and receives horizontally. So when we use the same polarization bands, we will have more energy to detect and higher quality. At least for these kind of tutorials, for these kind of estimations, we prefer to use same polarization bands. There are other properties available here. The property is those of information stored in the metadata. So one of the important properties here is, as you can see, is about orbiting paths, and also there are different parameters here. We have orbit properties paths. The orbit properties paths most of the time available with two situations, ascending or descending. The ascending and descending, they have two kind of different view for the region of interest. That's why we need to select only one of them, ascending or descending, for this tutorial. First, we want to see that which one of them is dominant, ascending or descending. It's very simple to check. Here you can copy and then inside the print through the aggregate properties, aggregate array, you can list all the orbit paths available for this region of interest. Run the code again. Now you will have a list same as number of images, but here mention that how many images are ascending or how many images are descending. There are two conditions here. So we need to select only one of them, or you can make two different variables, one for ascending and one for descending. So here, for example, I'm gonna select ascending first, and then we can make another one for descending data. So ascending should be selected, .filter, Earth engine.filter, .equal. I'm gonna use those of images, orbit properties path in which equals to ascending. So if you want to see only unique ascending or descending or unique properties, it's very simple. Just you need to use distinct. Run the code. In the right panel here you can see only we have descending now because we made a filter about orbiting paths equals to ascending. Or you can make two different variables in this regard. For example, a new variable as ascending equals to from Sentinel-1 data, add filter based on ascending. Now, if I run the code, the Sentinel-1 including ascending and descending together. And another variable here we will have for the descending data equals to from Sentinel-1 filter Earth engine.filter.equal orbiting path equals to descending. Orbiting path equals to descending. It is better to copy from the right panel to avoid any mistakes. So now the data is split into two different variables. One of them is ascending and the other one is descending. Let me to make a bigger space for the code. So print ascending data first. In the right panel, from 1300 images, 400 ones belongs to ascending mode. And now we can try it for descending data again to see how many descending images available. In the right panel, you can see around 900 of images belongs to descending mode for the orbit properties. This is a very important part when you are doing process. And sometimes for your region of interest, it is possible to have access to only one of the orbiting paths. Sometimes we only have ascending data and sometimes we only have access to the descending data. There is no problem. You can go through you can continue your process based on orbiting path that is available for you. But in case you had both of them together, same as this tutorial, you can make two different variables for each. So in the next step, I'm gonna do mosaicing and also I'm gonna make a multi-temporal data for the region of interest. As you know, the SAR data available every 7 or 6 days, but it depends to the latitude and also the region of the interest. But here I'm gonna show you how we can convert them to the 10 days data and also how we can do mosaicing for these 10 days or how we can get their average during this time period. It is very simple technique. Let me to make a bigger space for the codes. So now it's better. Make a new variable as a list of dates. List dates for the period of time in which Sentinel-1 data are available. So we need to make a list that should be applied for ascending and descending because we want to actually use this data ascending mode and descending mode with 10 days format and also in that is mosaic for this period of time. So list date equals to Earth engine.list.sequence, just like that. So couple of arguments we have here. The list is starting from 0 and ends to the differences or time differences between end and start. Make a new variable as time differences. Now I'm gonna calculate the days difference between time start and time end because I'm gonna make a list starting from 0 and end to the number of the days we have difference between time start or time end, or this is delta time. Time difference equals to, so time end first, then dot difference is a function help us to calculate the differences between time start and time end according to a unit. If you want to calculate based on a day to see that how many days we have during this time the unit will be day. Print time difference and run the code. In the right panel, you can see that 2556 days we have from time end to time start as the delta time. So the end will be equals to time difference, and the step is important. The interval for the multi-temporal composition we want to make is 10 days. So now I'm gonna make a 10-day interval here, just like that, and skip the count. Now print the list dates, but it is not. It is only including the number of the days and interval. As you can see, the data interval or the days interval is equals to 10, and also every 10 days we have one value. So now I'm gonna replace the values or number with the dates from starting date to the ends. So it's very simple. Just make a new function to do the replacement. So here the input is the delta or interval here, time interval. The function returning Earth engine dot date dot from year month day. Now I need to make a start date for this list. The start date equals to January of 2017. 2017 month January, day 1. Skip the time zone. And then from start we wanna go advance based on the interval or the difference. That advance from start go forward based on the delta. The delta here is interval and the unit is days. So run the code again. Again, we have a list with 256 dates that is starting from January 2017 and ends to December 2023. As you can see, there is a 10 days interval from one row to another row here. As you can see, this is 21, this is 31, this is 10, this is 20. So here we have a start date, and the list of dates now is available. For the next step, I'm gonna make actually 10 days data for the ascending mode. Let me to make a bigger space now. Bring actually scroll down a little, just like that, because I wanna write the code in the upper side of window. So a new variable for ascending data, I want to make the 10 days format equals to, so first the list of dates comes. List of dates comes here, and then I'm gonna make a function for each starting date. Now we need to make an end date and then filter the ascending or descending data based on the new start and new end date. So the function input is the dates, or you can choose any other name you prefer. So here make a new variable as start date equals to, so Earth engine.date. I'm gonna consider the dates as the date format first, and then the end date equals to, from start date go forward by advance with the delta 10 days interval, just like that. Skip the time zone now. So this is the end date. Now we have the end date, start date already defined. the end date now calculated based on the start date and interval function. So make a new variable. Now 10 days data equals to, or composite image equals to, get ascending data first, filter it based on new start date and end date, just like that, and get its average. The averaging technique do mosaicing and also doing mosaic process in the same time. Same time, you are getting an average from all of the data available during time start and time end, and then you calculate their average. The average is calculated here and it is mosaiced. So finally, function returns the composite as the final result. But the final image needs a new time start and a new time end. Here, .set allows us to make a new property explaining the time information or acquisition date for the new collection. We can make a new system time start based on new start date with millisecond format. Then make another system time end or a new system time end equals to end date with millisecond format, just like that. So print ascending data for 10 days. Write the code. In the right panel here, there is a list of bands available here that you can see for each 10 days, and sometimes during that 10 days maybe no images were available. That's why for some of the dates we have 0 bands. So if you want to have access to only VV band, and if you want to skip the other bands, it's very simple to select the target band from first. Select only VV bands. So, but select must be at the end, for example here, and then run the code. And remember to save it. Here, for all dates, 1 VV average for every 10 days is available, and with a new system time start and a new system time end with millisecond formats. And it is very important to get rid of the images with 0 bands, because it may actually lead to some sort of errors for the next part of calculations. So first of all, I need to convert it to an image collection format, because it has a list structure, and in the list structure we cannot apply those calculations related to the image format. So save your code and run it again. This time we have a new image collection with 256 elements. But the question is how we can get rid of the bands, get rid of the images with 0 bands. It is very simple technique. For example, here in the temporal collection function, or the 10 days data, we can make a new variable as bands equals to from composites dot band names estimate or returns the number of the bands. So now if you want to get the number of the bands, that size will be added here. Band name dot size helps you to estimate or calculate the number of the bands available in the composite, and then we can have this number as a new property that's set in the metadata. Band number equals to bands. So run a code again. In the right panel, again, we have same bands with a new property. This is the band number. Here, we only have one band number is 1. But here, there is no band number is 0. So it's very simple. We can make a new filter based on the new property that is created. For example, here, I'm gonna filter my data using earthengine.filter.equal. I need those of the images in which band number is equal to 1. Run a code again, and now you will have 254 images, and all the images available here only have one band, and those of images with no bands skipped or removed with the new filter or the new properties we created before. So you can try this variable or use this function for the descending data, but the only thing changed is actually ascending mode that should be turned to the descending mode. So here we have the descending data. This is the descending 10 days data equals to same list date and same structure, nothing changed except the ascending filter date. Here will be descending filter date. The data already filtered based on orbiting paths. So here now if I print the descending data with 10 days format, in the right panel you will see 247 images with 10 days interval. So now multi-temporal data created in this part. For the next session or next part, we want to do some sort of radiometric preprocessing. The reference I'm using for the soil moisture estimation is here, the paper entitled Toward Global Soil Moisture Monitoring with Sentinel-1 Images. In this paper, if you type or write this name on the net, you will find it in the Google Scholar as a reference for this tutorial and the equation that I'm suggesting you here. The final equation for the surface soil moisture, this is the target index for the surface soil moisture that help us to get an estimation with percent unit about the moisture content in the soil. So here and also here there are two parts. In the first part, this is delta sigma. Sigma naught here refers to the backscatter value. As you can see, it's explained here, all the parameters explained here, but simply the delta sigma naught refers to the difference between sigma naught in each date and also the minimum value for the whole period of time that I will show you how to calculate it. And also the second part is the S. Actually, the S is the difference between sigma naught for the wet and dry situation. The maximum sigma naught minus to minimum sigma naught. Because we suppose there is a relation, we suppose that higher backscatter values shows higher wetness and lower backscatter values shows actually lower redness. So, but for this tutorial, it is important to remove the water bodies and also the urban area to avoid any false information or errors during the calculations. Finally, I will show you how to skip urban area and water bodies to get rid of noises coming from these land covers. Back to the code, and now I need to calculate the sigma naught. As you know, the Sentinel-1 data available with decibel format. If you go to the data description in the Earth engine and read the description here, you will find information in this regard that mention that the data is available with the decibel format. But now I want to turn it from the decibel to actually sigma naught format. It is very simple in the Earth engine platform. So now I make a new function for ascending data that I want to make a new function to calculate the sigma naught. The sigma equals, so get ascending data with 10 days interval first, bring them into a loop using a function, each input image considered as an IMG here, and now I want to make a new variable as sigma equals to earth engine dot image 10 dot power to img dot divide 10. This is the equation to convert the data from decibel format to the sigma naught. This conversion is necessary for soil moisture estimation. So, in the next part, to reduce the spectral impact on radar data, it is helpful to use some sort of low-pass filtering technique to make it a little smooth and to remove the impacts of or adjust the impacts of spectral impacts that is naturally naturally you face with in the radar data. So a new variable for speckle here, I'm gonna do a smoothing process to reduce speckle impacts. So get sigma images then dot focal mean helps us to calculate the average focal mean. The radius is, for example, 30. When you use the radius such as 30, meaning that the spatial resolution, if it is 10 meter originally, reduces to 30 meter. And the kernel type here should be a square, and the units will be meters. Skip the other arguments here. So now the function returning speckle images, because it is already converted to the sigma naught, and also the speckle impact reduced by the low pass filter. It is speckle with the properties of input images. Dot property names. Here it is. Print ascending image that is converted to sigma naught already. So ascending sigma, name is wrong. Now resolved. So the sigma naught is calculated for each date and there is no problem. We can rename it as sigma. So repeat the function, this time for descending data. This is ascending, And now this is descending data. Descending with 10 days. Descending data equals to, instead of ascending 10 days, we will have descending 10 days, and also with the same equation. Nothing changed. So, save your code and check it out by print for descending image. Run the code. In the right panel, there is an image collection with 247 images. So, the ascending and descending prepared in Sigma-Nut and also speckle impact adjusted using the low-pass filter. For the next part, we need to calculate the minimum value and the maximum value of Sigma-Nut images during the temporal period that we are doing the processing. So now ascending mean equals to a new variable. First, ascending minimum equals to ascending sigma comes here, dot minimum. The minimum is a function calculates the minimum Sigma-Nut value for each pixel. Here we suppose the minimum equals to the actually dry situation. The minimum equals to the dry situation, and the maximum equals to the wet situation. So this is the minimum value for each pixel, and then we will have ascending maximum equals to, again, ascending sigma dot max. This is a representative for the dryness, and this is a representative for the wetness here. So after then, we need to calculate the equation. So now we need to calculate this in the Earth engine. In the first part, each ascending or descending data with 10 days interval must be subtracted from the minimum value and also then divided to the difference between maximum and minimum Sigma-Nut value. So here, back to the code, ascending soil moisture equals to get ascending Sigma-Nut image first and then bring it into a loop and do the calculation using a function. Each input image in the function consider it as an IMG, make a parenthesis, and finally do the calculation using index. Index equals to, so now there is a parenthesis that is divided to the second part. The second part is the difference between ascending max dot subtract from ascending mean, just like that. And then the input index is each IMG that's subtracted from the ascending mean. This is the delta Sigma-Nut. The delta Sigma-Nut and the difference between wet and dry. So, but it is important to remove or get rid of the water bodies and urban area in the final data. Finally, function return soil moisture as an index here, but we need to get rid of the urban area and water bodies. To do this, we need to make a land cover map for the region of interest and then remove the water bodies and urban areas using update mask procedure. So now I'm gonna make a new variable as land cover, or a new variable for water mask equals to, go to search places and dataset and try to find dynamic word land cover data. The dynamic word land cover data is one of the wonderful products available in the remote sensing community and Earth Engine platform. Enables us to have access to dynamic land cover data with a 7 days interval based on Sentinel images for all around the world. Import it into the code, and then I'm gonna make a unique land cover layer for the region of interest, and then remove the urban area, remove the water body from that. So the second image collection equals to the land cover, and then I'm gonna select it for the years I'm doing the process. That filter date first because it is a dynamic and changes temporally and spatially. Filter date equals to time start and time end, and then limit it to the region of interest by filter bound based on the geometry or region of interest. So if you go to the data description, Google Dynamic Word, in the bands you will see that there are different bands available here. One of them is the label, including all the bands next to each other in a single layer. So the water, the value 0 shows the water bodies. So I'm gonna select the label and select the pixels with 0 value. To select the band, we need to use .select label band. But if you want to make a unique land cover or integrated land cover based on the temporal period, you can get the mode, the most frequent classes assigned to each pixel. And then I'm gonna select those of pixels equals to 0. So this is a binary image now. The values number 1, pixels with number 1 show the water bodies, and pixels with number 0 shows the other land covers. But as I want to use this as a mask layer, I need to change it in the actually in another value orders. I want to have value 0 for the water bodies and value number 1 for the other land covers. To do this, .not must be used. So use the same one for the urban area. The urban mask, the only thing changed is the number of pixels, is the value of pixels. Go to the data description for the dynamic word, and here you can see the built-up area including value number 6. Now I'm gonna make a mask layer for pixels with value 6. So in the next step, we need to combine these masks together into a single file, or we can apply them on the index that is calculated before. No difference. You can combine them in the same layer, or you can apply them separately 2 times. So for example, .update mask. You can use the update mask, or you can use multiply. For example, this is an image with values 1 and 0. When you do the multiplication, meaning that those of pixels with 0 value for the water and urban area cause the 0 value in the final result, or no data for the final result. This is the multiplication. It is the simple format. Or you can use the update mask. No matter. You can use both of methods. So multiply face water mask, and then do multiplication again, this time for airgun mask. Return it with the properties of input images. So print ascending soil moisture. This is calculated. Save the code and run it. A new image collection including soil moisture data calculated. This is not sigma anymore. Actually here it is got rename. It is soil moisture with ascending data. Run a code again. In the right panel, again 254 images is available, soil moisture with ascending, and now you can have a visual you can have a visual test for the output that is calculated. So equals to map.addLayer, helping us to do the visualization. I'm gonna do the visualization for the ascending mode, but only for a 1 year. That filter date, I'm limiting it to 1 year, for example 2020, and then I'm gonna stack them into a layer. That clip, I'm gonna clip them based on the region of interest. Leave the visualization parameters empty. The layer name is soil moisture ascending, and use the false at the end. The false help us to avoid automatic visualization that highly reduces the speed of processing. So, and if you want to see the date of each image next to the band name, you must make a new property here. A new property is date equals to, from input image, I'm extracting the date or correspond date and convert it to the string format with year, month, and day structure like this. And I'm gonna make a new system index property using set. The new system index equals to the date, but it must be with a string structure. Run a code again. Let me to print it again. Ascending soil moisture data. And remember to save the code. 254 images available, soil moisture for ascending, and also here we must have a new system index. That copy system index equals to date. I don't know why it doesn't work, because we must have it as a new collection, as a new property here. Let me to try it again. Just let me to change something in the copy properties. For example, here I'm gonna have only system time start with this new system index. Anyway, if the problem still exists, you can make a new property with a new name. Instead of system index, we can have a new property as date and run the code. Then you will have a new property as a date format that shows the start date for each image. So the problem is solved. Now go for the visualization. Go to the Google Map, save the code, remove the geometry, zoom to the region of interest, and turn it to the satellite view. You can see that we have a water body, we have a cropland, we have urban area, and soil. Click on soil moisture for ascending data, go to the layer setting, And here you can see the soil moisture for the 2020 is available. For example, I'm selecting one image here. We need wait for the range of value to be updated, then click on apply. Here, the regions with the higher values shows with the white color, and the regions with the lower values or lower soil moisture actually reflect is shown with by darker region. So the regions with higher vegetation content shows higher moisture. The region with no moisture content without vegetation content or vegetation cover shows lower soil moisture values. So this is the soil moisture image that is created, and then I can make a new geometry to assess the variation of the soil moisture for that point. And also the water bodies, for example, here is removed, but this part not removed because I know this area, this is covered by vegetation cover. That's why not detected by the satellite as the water body. And here you can see in the agricultural area, we have the higher values. So now I'm gonna select a region to assess the moisture variation during a time. For example, I'm gonna select this region, and then we can make a plot for. So here, to make a plot, it is very simple. Make a new print. Inside the print, user interface dot chart dot image dot series. In a couple of arguments available here. Instead of image collection, we will have ascending mode or ascending image or ascending soil moisture. The region is geometry number 2, and the reducer is average Earth engine dot reducer. That means the scale equals to, if your region of interest is a little big, same as what I have, it is better to set it to 100. But in case your region of interest my region of interest is geometry 2, it is a small, then we can set 30 as the scale value, and the property will be equals to system time start. Run a code again, and then you will have a chart shows soil moisture variation based on ascending data. You can have a same code for descending images. Just let me to here, this is the soil moisture variation. As you can see, this is an index and ranging from 0 to 1. It is based on percent. For example, 60% or 0.6. If you want to convert it to the percent, just you need to multiply it to 100. So then I'm gonna do this for the descending data. It is very simple, just we need some small changes. Instead of ascending, we will have descending image. This is again the descending sigma, and all the ascendings converted to the descending. Soil moisture for descending. Here it is. Save your code and run it again. descending soil moisture. Oh, it is still ascending, and let me to change its name. This is descending mode, and run it again. Now we will have two charts, one of them for ascending and one of them for descending mode, that shows the soil moisture variation for the region of interest. And you can use them for your own studies, and the values are different. That is completely normal, because the type of imagery and all the direction of the imagery or the angle view for the ascending mode and descending mode is different. That's why you can see the different values for the soil moisture for the same region. So if you want to get export with TIFF format from ascending or descending data, you can use export.image to drive. So the image I want to get export equals to, for example, descending soil moisture for 2020, got two bands, and then clip it based on the region of interest. Then description shows the output file name, descending soil moisture, scale equals to 30, because after the spatial process, spatial resolution reduces to 30 meter. Region of interest is geometry. CRS coordinate system equals to EPSG 4326. This is the code we use for WGS84 soil moisture coordinate system. And this is the CRS, and you can set a target folder to save your data in the Google Drive, and the other parameters, description, scale, region, CRS, I think everything is done. And also the max pixel is another one. The max pixels, the maximum pixels you allow to save in a single TIFF file will be Earth Engine, 1E13. And you can use export.image, same as we have for descending data. For the ascending mode, the only thing changed is the name of the input here. Save the code again and run it. In the right panel, after a few moments, you will have a new task here as descending soil moisture. Click on run, and then you can save it into your Google Drive. So here it is, and hope you like this tutorial as much as I did. And I tried to give you inspection about soil moisture estimation index using Sentinel-1 data. That is very, very valuable for agricultural studies. If you had any problem regarding to the code, no worries. The code link is available below the video in the chat, in the description box on my YouTube channel. If you had any questions, you can reach me out on comment on my YouTube channel in the comment part. And thank you for your attention.